And this is Lab 4, Oscillations. So the purpose of this lab is to analyze the motion of a mass spring system by comparing the predicted and observed motions in both the x and y directions, using the measured calibration length, time between video frames, and known physical characteristics of the system, including mass, spring stiffness, and relaxed length. This experiment aims to model the system's behavior and validate it through experimental data. Additionally, the lab investigates the energy transformations within the system by plotting changes in kinetic, gravitational, and spring potential energy and total mechanical energy over time. I apologize for the digression, but some of the key physics principles are the Newton's second law of motion. So the second derivative of the x position over the derivative of time squared, which equals the k spring times x, or the change in position of x. So it's the net force acting on the oscillating system, which equals the mass times acceleration. Then simple harmonic motion, or rather known as SHM, is the displacement, velocity, and acceleration of the mass in a sinusoidal method that you'll see in a later on slide. The period of t of frequency and f depends on the system's parameter. So 2 pi square root of the mass times the k spring. The conservation of mechanical energy. So an ideal frictionless system. So we use, there's no friction really in this system because it is a spring. So E total equals the E of kinetic energy plus potential, which is just 1/2 mass times velocity squared, plus 1/2 the k displacement squared. So as a result, the oscillatory motion of the spring mass system was analyzed both experimentally and computationally using tracker systems. The position of mass A was extracted in both the x and y directions as a function of time. The resulting data showed a clear periodic oscillation, characteristics of simple harmonic motion. From the plots, the period of oscillation was approximately 2 seconds, and the amplitude in the x direction reached around 10 meters, or 0.10 meters. While the y direction oscillated between negative 0.75 meters and negative 0.65 meters. These sinusoidal patterns confirm that the mass experienced a combination of horizontal and vertical oscillation influenced by both spring tension and gravity. To further analyze and validate the observed motion, Python was used to model the same system computationally. The Python generated plots comparing the predicted and observed positions in both the x and y directions and showed graphs according to energy. Overall, the combination of video analysis and Python modeled providing consistent and complementary results, obviously demonstrating the relationship between position, time, and energy in the mass spring oscillation system. So this is basically the tracker. In tracker, we analyzed the video. I used a calibration system and calibrated it to 0.7 meters between the center of mass of the object and the spring itself. Then the mass of it was pinpointed in different periods of time over the video. As you can see to the right of the video, there is a sinusoidal motion that you can see as a result of the data being tracked. So here's the coding for the Newton's second law in terms of and the graphing for energy change, as seen to the right. So K initial, or K gravitational potential, spring potential, and energy was all initialized and then run through a while loop and done that way and all graphed. And then here are the graphs resulting. As you can see, it's a change in energy in the top and the x and y positions graph below. The change in energy, you can see the delta U, or the change in gravitational energy, the change in spring energy, and the change in kinetic energy, all graphed there. And then you can see model versus experimental, sort of the differences. As you can see, there's not much difference between the both. So in the experimental method, we were able to achieve a predicted motion. So results and applications. Based on the energy plots resulted in the Python, the energy principle is largely satisfied for the model spring mass system. The graph of energy versus time shows clear oscillations in the kinetic energy, gravitational potential energy, and spring potential energy that alternate as the mass moves through its cycle. When the spring is at max compression or extension, the spring potential energy is greatest while kinetic energy is minimal. Conversely, as the mass passes through the equilibrium position, kinetic energy reaches its maximum while potential energy decreases. The total mechanical energy remains nearly constant throughout the simulation, confirming conservation of energy within experimental limits. Small fluctuations in total energy are observed and can be attributed to a dampening effect, air resistance measurements of uncertainty in both tracker and the simulation model. Overall, the consistent total energy indicates that the energy principle holds true for the oscillatory system. Thank you so much for listening, and yeah. Additionally, using the tracker position from data, 2 independent periods were estimated. So from the X versus time, it's about 2 seconds per cycle, and from the Y versus time, it's about 2 seconds per cycle. The close arrangements between X and Y confirm the motion is coupled by synchronized directions in both consistent and spring mass system oscillation.